So let's take a look at this example problem here. In this example problem, we have two planes flying towards each other. So we can see we have plane A over here coming down at 35 degrees off the horizontal. Plane A has a velocity of VA is equal to 600 kilometers per hour. And over here we have plane B. Plane B is flying towards plane A and has a velocity of 700 kilometers per hour. Now, something to think about as we see this given diagram in the problem statement is how we want to set up our coordinate system. Do we go with a standard Cartesian coordinate system where we have y positive going up and x positive going to the right? Because if that's the case, if our x positive going to the right, then plane B is going to have a negative velocity in the x direction, and plane A is going to have a positive x component of the velocity. Now, if y was positive going up, then A would have a negative y component and B would have a zero y component. So we need to really consider that when we set up our coordinate system. What's positive? Is x positive right or x positive left? Is y positive up or y positive down? So within this, we know velocity A, 600 kilometers per hour, velocity B, 700 kilometers per hour. We can establish the direction when we choose our coordinate system. They want us to solve for the velocity of B relative to A, so we have a relative velocity problem. Plan of attack for solving this problem. Use the vector method. We could write out the vectors VA and VB in Cartesian form and then determine the velocity of B minus the velocity of A for the two vectors. B, option for a graphical method. We could draw vectors VA and VB from a common point, apply the law of sines and cosines in order to determine our velocity of B relative to A. So two different methods to arrive at the same answer. So now the first thing we want to do as we begin our solution to this problem is create our setup page. So we take all of the given information from the problem statement and the initial given diagram, write it down on one page in a clear and concise manner so that we can reference back to it as we're going through the solution to our problem. So you can see here I redraw out my diagram. I have plane A coming in here, velocity of A, angle here of 35 degrees off the horizontal, plane B coming in right here, VB right there. I know that my plane A has a velocity given to us in the problem statement is 600 kilometers per hour, acting in this direction here. And I know that plane B has a velocity of 700 kilometers per hour, acting in this direction here. We know that we need to solve for VB/A, velocity of B relative to A. So as we mentioned previously, the first thing we really want to do is establish a coordinate system with this here. So for nothing popping out at me as, okay, I definitely want y positive down or I definitely want x positive going to the left, if nothing really jumps out at me, I just go with my standard Cartesian coordinate system here where x is positive to the right and y is positive up. So we'll start with that, and if we go through the problem, we see we have a lot of negatives and double negatives, and sign convention becomes a bit of a nightmare. We can go back and switch this. But for now, let's just start with our standard Cartesian, x positive to the right, y positive going up, which means our velocity at B is going to be in the negative x direction, and our velocity at A is going to have components in the negative y and the positive x directions. So next we're going to look for these two methods that they asked us to solve this with. First, we're going to have our vector method. Second, we're going to have our graphical method. So for our vector method, we're going to need to write out our velocity vectors, v sub A and v sub B, in Cartesian form, and then determine the velocity of B minus the velocity of A vector. For our graphical method, part B, we're going to draw out these vectors, vector A, vector velocity of A, vector for the velocity of B, from a common point, and then apply the law of sines and cosines to determine a velocity vector of B relative to A. So now we have an entire setup page. We have all of our given information, our given diagram, our chosen coordinate system, our plan of attack for the two methods in order to solve for what they ask us to solve for. So we can always reference back to this page as we're going through our solutions. So now that we've chosen our coordinate system here as x positive to the right and y positive up, we realize the velocity at B is purely moving in our x direction and in the negative x direction according to our chosen coordinate system. But our velocity at A is going to have both an x and a y component, where it's going to have a negative y and a positive x. So I look at this here, okay, here's my velocity of A right here at 35 degrees off the horizontal. Well, here's my y component going down, negative y direction, VAY, and my x component here, VAX, going in the positive x direction here. Call my rules from trig over here. SOHCA, TOA, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Here's my angle here, here's my opposite, there's my hypotenuse, and there's my adjacent right there. So I've clearly labeled this all out, make my life nice and easy, do this all separate from the actual problem so that I don't have to include this in a big nasty equation. So look at it, okay, let's take a look at my y direction first here. So I say again, y, if we want to deal with this guy here, sine of 35, sine is opposite over hypotenuse. There's our y over hypotenuse, VAY over VA. Plug this in here, we can rearrange and solve for our VAY component. We do that, and we say that VAY is equal to our velocity vector VA times the sine of that 35 degrees. Well, we know that this is given to us in the problem statement as 600. So we can plug that in and we realize it's going down according to our choice in the coordinate system, so we don't forget our negative value there. VAY is equal to negative 600 times the sine of 35 degrees. Now we can do the same thing in our x direction here. Take a look at this. Okay, we now have our cosine. Cosine is adjacent over hypotenuse. Adjacent over hypotenuse. There's my VAX over my VA right there. Rearrange, solve for my x component of velocity. VAX is equal to VA times the cosine of 35 degrees. I know again my VA was given to me as 600 here, so 600 times the cosine negative 35 is moving in our positive x direction here, so we pay attention to our sign convention. So from this here, I now have my x and my y components for my velocity of plane A. So now we want to go through our two different methods for solving this problem. We had method A and method B, where method A, that asked us to use the vector method. So within this vector method, we wanted to write out our vectors v sub A and v sub B, and we went through and found those and solved for those using our trig triangle on the previous page of our solution. We found that velocity of A vector is equal to 600 times the cosine of 35 minus 600 times the sine of 35. We have your x components and your y components there. Again, we can look at this, okay, this is going down in the negative y direction and over in the positive x direction. We can always go back and reference our setup page here. Velocity of A going down in the negative y, positive x, according to our chosen coordinate system. So our sign convention is correct here. Positive in our x direction, negative in our y direction for this v sub A. Do out our math on this. 600 times the cosine of 35 is equal to 491.5 in the x direction, minus 344.1 when we do the 600 times the sine of 35 in our y direction, negative, because it's going down our negative y, according to our coordinate system. Units, kilometers per hour. So now we want to do the same thing for plane B, so our velocity vector B here. Well, if we go back to our setup page, we can see B is moving purely in the x direction, and it's in the negative x direction. We're going to have a negative 700 kilometers per hour there. Again, velocity B moving purely in our negative x direction. So drawing these little guys often helps. Even though we can reference back to the first setup page, it's nice to have these two guys here to quickly look at it and do a double check in our head to make sure we have our sign convention right. So now that we have this velocity vector for velocity of A and B, we now want to do our math here and subtract velocity of B relative to A is equal to velocity of B minus the velocity of A vectors. So I take and go up here, there's my B, there's my A vectors there. I can see that B only has the x components. So this is why unit vectors are nice, because we can quickly look at this and say, okay, this is in the x direction, our I hat direction, our unit vector here. There is no component in our j hat or our y direction for this here. So I want to take care of things individually by components. So I can say, okay, deal with my x components first. Negative 700 minus 491.5 gives me negative 1,191.5 in my x direction. So I do the same thing in my y direction over here. This is 0 minus 300 minus a negative 344.1 becomes a positive 344.1 in our y direction there with units of kilometers per hour. So if I wanted to find the magnitude of this vector here, I'd take the square root of the sum of the squares of the individual components. Square root of 1,191.5 squared plus 349.1 squared. We do that out, and then for the scalar of this here, if we take the magnitude of this, is 1,240.2 in units of kilometers per hour. We can find that angle here, do a little bit of trig here. When we come up with this, okay, we have our two components here, inverse tangent of negative 344.1 over 1,191.5. Back that out, get our theta value there. Do a little bit of trig over here. Again, and go back to the second page of our solution. take a look at what we're dealing with for our components from here. If we want to look at a bigger one, I would suggest always doing that if you're not quite sure of your trig and you don't want to do these quick little small checks for your components over here. You can go back to your bigger one or do it on a separate page if you need to for that trig there. Prove yourself that you're using the right components for the trig that you're doing here. So in this case, inverse tangent here. From that, we can then get that this angle here between velocity b relative to a is going to be at 16.1 degrees with a magnitude and a direction. So two different ways to express the answer here. We have the vector form, we have the individual components of the vectors written out in here with your x and your y, or we can give it to it in terms of magnitude and direction. So let's take a look at our method B here. Our method B that asks us to solve using the graphical method, where that asks us to put the vectors drawn out as our vector B and our vector A from a common point. So here's our common point right here. So you can see vector B coming off this common point in the pure negative x direction, velocity of A coming off this common point, and a positive x, negative y direction right there. And we can calculate this angle because if we know that A came off the horizontal over here when it was coming in here at 35 degrees, and this is drawn down here at 180 degrees now, so 180 minus 35 would give us this 145 degrees between these two vectors right there. Then we can draw a vector for our velocity b relative to A from the tip to tip here, from A to B over there. So then we end up with our graphical representation here for velocity of B relative to A. So what we want to do from here now is take a look at our law of cosines and our law of sines. So what we can do, let's quickly reference back to what those are. So if we reference back to those equation sheets that I uploaded for you guys previously on Blackboard, we can see down at the bottom of the second page here, we have our law of sines and our law of cosines and our relative position. So this is always a great spot to reference back to if you're not sure where to start these problems. You can see your graphical representations, you can get your vectors as well. But what we want to look at now is this bottom portion here for our law of sines and cosines. So we have angles with the capital A, B, and C inside here. We have our sides, lowercase a, b, and c here. So our law of sines simply says that A over the sine of A, which is side A over the sine of angle A here is equal to B over B is equal to C over the side of C here. So this is our law of sines. Our law of cosines, with three different versions of this here, depending on what we have. So this is important. Take a look at what you're given for your problem and pick which one of these three relationships will work for you. You have the correct number of unknowns and knowns. So we have a squared is equal to b squared plus c squared minus 2bc times the cosine of A. B squared is equal to a squared plus c squared minus 2ac times the cosine of B. And c squared is equal to a squared plus b squared minus 2ab cosine of C. So this is the refresher for our laws of sines and cosines. So now let's go back to our problem and implement these. So let's go to our law of cosines, where in general terms we go with the first one here. The a squared is equal to b squared plus c squared minus 2bc times the cosine of A. So if this is our side A and our angle A here, we have here, according to this thing, our side A here squared, which is our velocity b relative to A squared, is equal to b squared plus c squared, our two sides. There we have over here our b squared and our c squared right there. Add those two together, minus 2 times BC, well, there's your B and your C right there, 700 and 600, times the cosine of A, where A is this angle here, which is a cosine of 45. So that's all we've done is taken our law of cosines, applied to this one here, where we have our A right here, and then our B and C is on the sides over there. We can plug that in, and what we end up with when we do out our math here is the velocity of B relative to A is equal to 1,240.2 kilometers per hour, which, if we go back up here, to our method from part A, where we solved the vector method, our magnitude here was exactly that. So the first part from the law of cosines, we solved for the magnitude of the velocity b relative to A. Now what we need to do is use the law of sines in order to solve for our direction. So we have magnitude and direction. We have the magnitude, now we need to solve for the direction. So how do we do that? This is by using the law of sines. So if we recall from the law of sines, we had A over the sine of A is equal to B over the sine of B is equal to C over the sine of C. So we have A over the sine of A is equal to velocity of A over the sine of A there. So we have this over this is equal to this over this here. So now we can cross multiply with this here. So VA times the sine of 45 is equal to V sub BA times the sine of theta. Do out the cross multiplication here. We can solve for our V sub A. We can plug in our value now that we have for V sub B over A that we just solved for there into this here. And what we end up with is theta is equal to 16.1 degrees for our direction, which is exactly what we solved for above using the vector method. So either the vector or the graphical method work just fine. Depending on what your preference is, what you're given in the problem statement, one may be more straightforward than the other.